Hi folks, welcome back to another lesson, and we're going to start a new topic which is forces. It kind of ties in a little bit with our space because the very first one we look at is weight, mass and G. So we're going to define the force and what it can do, define weight and mass, determine and state the relationship between weight, mass and G, calculate weight on different planets and explain whether weight or mass changes. So quite a lot of stuff. And we'll be working from your workbooks and your physical learning outcomes that you already have in your folders. So those stuff are there. I'll put them on the Teams as well, just to make sure you've got a copy if you've lost yours already. So first of all, a wee question for you is: if my Lamborghini weighs a ton, is it heavier than a ton of Skittles? Okay, so have a wee think, pause the video, have a wee think. Um, Hopefully, you've been able to answer that, and the answer is that if the Lamborghini weighs a ton and the Skittles weigh a ton, then they should both really be the same weight, right? They're both the same heaviness. But then that brings in the question of what do we mean by weight, right? What is weight when we say something weighs 100 tons and if something is heavier or lighter? So some very kind of interesting questions we could ask around weight. So to start talking about weight, let's talk about forces, which sounds a bit weird. So the definition of a force, and I would like you to copy this into your jotters, is the following. A force is a push or a pull that causes a change in shape, direction, and acceleration. So there are three things that forces can do. They can change the shape of an object, they can change the direction of an object, and they can accelerate an object. Okay? And what we're going to do is we're going to look at these three things over the next couple of lessons. If you don't believe me, take a scrap piece of paper and you can scrunch it up, which changes the shape of it. You can throw it and then suddenly kick it, and that means you can change its direction. And if you throw it really hard, you can make it accelerate. So that's what a force can do. So force has units of newtons. So it has the symbol F. So that's the symbol we would write to write instead of the word force. And the units, just like the unit for distance is meters, is in newtons, which is represented by a capital N. And it's named after Sir Isaac Newton, who did a lot of work on forces. So weight is a force due to gravity pulling on an object. So again, I would like to write this down, and this is the definition of weight. And this is a physics definition, and it's very specific because we use weight and mass in our everyday language to mean the same thing. But in physics, weight is a very specific definition. Weight is a force due to gravity pulling on an object. And that's a definition I want you to remember. So if I ask you what is weight, then the answer you tell me is that it's a force due to gravity pulling on an object. Now, if it's a force, what units do you think the weight will have? Well, if weight is a force, then it must have units of newtons. Okay, and the famous story is that Sir Isaac Newton was sitting underneath a tree and an apple fell on his head, and that's how he started thinking about gravity. Now, I very much doubt an apple fell on his head because it's quite sore. It's more likely the apple maybe just fell close by to him. So, if weight is a force due to gravity, then what is mass? Well, mass, one way to think of it, and it's not the only definition, is how much stuff you're made up of, and it's measured in kilograms. So make sure you get this clear in your head that weight and mass are two separate things. The two separate things, firstly, because they have two definitions, different definitions, and also they're measured in different units. Weight is in newtons, mass is in kilograms. Okay, so make sure that you are aware mass and weight are not the same thing. They're two completely different things, but in our everyday language, we are actually using them to mean the same thing. But in physics, it isn't. So make sure you're clear about that in your head. Okay, now, if we were in class, we would do this investigation. You may have done this in first, second year. So I'm just going to skip over this and we can do this when we get back into class. Now, how do we calculate the weight? Well, weight is given by this equation, and you'll notice this equation is one of the equations in the very front page of your workbook. It's given by weight is equal to mass times g, where g is the gravitational field strength of the planet. Weight is in newtons, as we know already. Mass is in kilograms as well, as we know already. And gravitational field strength has as units newtons per kilogram, and that's how you pronounce it, newtons per kilogram. And you can write it as either way. I tend to type this because it's easier, but you can write it as this as well, and you'll be fine for either unit. Now, the key thing we need to remember is that G on Earth is 9.8. So this tells us how strong gravity is on Earth, and we'll look a little bit more about gravitational fields later on. But on Earth, you have a gravity of 9.8 newtons per kilogram. So let's look at how we can use this to calculate weight. Now, the only thing I want to add before I move on is that G does change depending on which planet you're on. So G is only 9.8 on Earth, but on the Moon it's a lot lighter, it's 1.6. And we'll look at the G of other planets and how that ties in with weight and space travel a bit later on. So here's your worked example, folks. A boy has a mass of 56 kilogram. What is his weight on the Earth and the Moon? So usually you're given the value of G. If you're not, you will get a data sheet where you can look it up to see what the value of G is for a specific planet or the Moon. Okay, so to do the calculation, pretty straightforward. Remember, we're using a KFC technique. We write down what we've got, write down our equation, plug in our numbers, and then calculate it. Now, I've rounded this to the nearest whole number, so that way it's a bit of a nicer number to talk about rather than talking about decimals. I would like you to try and do the same. So if you get an answer that's got decimals, try and round it to the nearest whole number. So that's the weight of the boy on the Earth. What's the weight of the boy on the Moon? So we do the same calculation. But notice how we've swapped G for 1.6 because he's now on the Moon, and it's a lot lighter. Okay, it's a lot smaller. Now, if we look at the two answers, you can see his weight is different because on the Earth it's heavier than it is on the Moon. But did the boy's mass change when he was on the Moon? Okay, if we think about it, look at your answers and think about is it yes or no. Hopefully you said no, because if you look at it in both calculations, we use his mass as 56 and 56. So your mass doesn't change unless you change a part of your body. So for example, if you were to cut an arm off, and you lose that arm, then your mass would get lighter. Okay? Your weight will always change depending on which planet you're on because it depends on the value of G. So an astronaut who leaves Earth to go to Mars, their mass would still be the same, but their weight would be different because G on Mars would be different. So that famous weight loss club called the Weight Watchers is really wrong because you're not really losing weight, you're really losing mass. So we should really rename that Mass Watchers. Okay, so just to summarize that, so if you could write this down, folks, weight depends on G, so it depends on where you are. Mass doesn't depend on G, so it doesn't change. And I would really underline this one because this is the bit that people tend to forget. So what's your mass? So feel free to measure your own mass if you've got a pair of bathroom scales, and then we can work out your weight on the different planets. So as a wee exercise, I'd like you to try and work out your weight on different planets: Mercury, Venus, Mars, Jupiter, Saturn, and Neptune. Remember, you are using the equation W is equal to mg. Okay, now if you don't have bathroom scales or if you don't want to weigh yourself, then that's fine. Just take your mass to be the mass of an average person, which is reckoned to be about 60 kilograms, and do the calculations for those different planets. And what you'll find is that Jupiter is the biggest planet, so your weight will increase if you go to Jupiter. Mercury is the smallest planet along with Mars, so if you went to Mercury, your weight would get less. However, your mass, in this case 60 kilograms, would still stay the same regardless of which planet you're on. So calculate weight if you were on each of these planets. Does your mass change if you went to each planet? And the answer to that is hopefully you're going to tell me is no. Okay? And there's some really interesting things about gravity, but we'll talk about that when we get back to school. So, gravitational field strength. What do we mean by this? So how does an apple know how to fall towards the earth? Because if you think about it, when an apple falls from a tree to the ground, there isn't anything telling it to do that. There isn't anything telling it it's got to go down the way. Why doesn't it fall up the way? Why doesn't it fall sideways? Why does it fall down at all? Okay, so one way physicists explain this is by using this idea of a gravitational field. So you can imagine Newton sitting there, he was probably asking the same questions. Why did that apple fall down? What caused it to fall down? Now, a gravitational field is this. If you imagine this is planet Earth, then around planet Earth there are these imaginary lines, just like the arrow, which extend out the way, but they all point towards the Earth. And these lines here represent gravity. Okay, so these lines represent gravity and the arrows represent which way gravity is acting. So you can see from this diagram that gravity surrounds the Earth and it's telling things to go towards the Earth. So these are imaginary field lines, they don't really actually exist, and they exist around every mass. They tell gravity how to act. So what I would like to do, folks, a wee bit of copying, is copy the diagram. Obviously you don't need to do a perfect Earth like this, just a big circle and call it Earth would be fine. And copy these two lines as well. Now, these field lines exist around every mass, so technically there's a gravitational field around you and you're actually attracting other masses to you. Okay, now you might say, well, why can't I hold my hand out and attract a pen to my hand? And the reason for that is, sadly, your mass is actually really, really small, so your gravitational field is also really small. So, yep, you could be pulling that pen to you by the slightest amount, but it's not enough for you to notice it. In order for it to actually have any effect, you've got to be about the size of a planet or the moon. Okay, so another way to think about this value of G then is the gravitational field strength. So it literally tells us how strong gravity is. Okay, so I would like you to copy this bit down again. G is the gravitational field strength. It measures how strong gravity is. It has units of newtons per kilogram. So the bigger the value of G, the stronger it is. So for example, G on Jupiter is 24 newtons per kilogram, whereas G on Earth is 9.8 newtons per kilogram. So G is stronger on Jupiter, which makes sense because Jupiter is a much, much bigger planet than Earth, which you kind of remember from that video I showed you about the different size of objects in space. So just to summarize that, bigger masses will have a stronger G, bigger masses will have more field lines around it. So the more field lines there are, the stronger the G. And again, if you could add this to your notes, maybe draw this diagram again so that you can see more field lines means a stronger G. So just to get you to think about it a wee bit more, G fields, these gravitational field lines, stretch out to infinity. That's how physicists imagine these lines work. So in my diagram, I should really be drawing this out all the way forever and ever and ever. That's what infinity means in this case. So two questions for you. Does gravity ever disappear? And what is weightlessness then? Is weightlessness when you have zero weight or zero force acting on you due to gravity? Have a wee think about that. If you think you know the answer, email it to me. We'll discuss this maybe at the tutorial on the Wednesday. Now, just to finish this off, field lines, you've probably seen them before because you probably know about magnetic field lines. So these are field lines which are around magnets, and they kind of do the same thing as gravitational field lines, except they tell other magnets whether to be repelled if they're both the same, or to attract if they're opposite. And you can see here from this field line here that negative is attracted to the, not the negative, sorry, the north is attracted to the south because the field lines actually go from north to south. Whereas if you had a north and a north, you could imagine the field lines would actually repel each other, or they wouldn't actually line up. So that means it tells the North Pole to repel from the North Pole.